Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in, to let your body find its most comfortable position, to release the weight of the day. There's nowhere else you need to be. Where in the world are you watching from? A quiet room where the stars might be visible through your window? A cozy space where the universe feels both impossibly vast and somehow intimate? Tonight we're going to explore one of the most profound mysteries in modern cosmology. Structures so large they shouldn't exist according to our best theories about how the universe works. We're talking about cosmic walls billions of light years across, filaments of galaxies stretching farther than light could have travelled in the time available to create them, patterns in the universe that violate what we call the cosmological principle. We'll discover how astronomers found these impossible structures, understand why they challenge everything we thought we knew about the universe's formation, and contemplate what they might reveal about the nature of space, time, and cosmic evolution itself. But don't worry, this isn't going to be an alarming revelation about cosmic catastrophes or a breathless race through complex calculations. Instead, we'll move slowly and carefully through the story of scale, taking our time with each discovery, each gentle paradox, each quiet insight into how the universe organises itself at the largest possible distances. By the end, I think you'll find that these impossible structures aren't really contradictions, but invitations to understand the cosmos more deeply, more subtly, more completely. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. These documentaries exist because of viewers like you who appreciate slow, thoughtful journeys through space and time. And to those already subscribed, thank you for being here, for trusting these gentle explorations of the universe's deepest questions. So settle in now, let your shoulders drop, take a slow breath in through your nose, and let it out even slower through your mouth. And let's begin our slow drift through the largest structures in the universe, through scales so vast that human minds can barely comprehend them, through patterns that shouldn't exist but do. Waiting quietly in the darkness of deep space. There's nowhere you need to be right now, nothing you need to solve or understand completely. Just listen, and let the story of cosmic structure unfold, patient and vast as the universe itself. In 2013, a team of astronomers led by Istvan Horvath announced a discovery that sent ripples through the cosmological community. They had found a structure so large, so impossibly vast, that according to our best theories about how the universe evolved, it simply should not exist. They called it the Hercules-Corona Borealis Great Wall, and it measures roughly 10 billion light-years across, making it the largest known structure in the observable universe. To understand why this discovery was so troubling, we need to first grasp the scale we're talking about. A light year is the distance light travels in 1 year, about 6 trillion miles. Our Milky Way galaxy is roughly 100,000 light years across. The distance to our nearest major galactic neighbour Andromeda is about 2.5 million light years. These distances already strain human comprehension, but they're tiny compared to the Hercules-Corona Borealis Great Wall. 10 billion light-years is more than 2,000 times the distance between the Milky Way and Andromeda. It's roughly 7% of the diameter of the entire observable universe. The structure is so large that light, travelling at its cosmic speed limit, takes 10 billion years to cross from one side to the other. When the light we see from one edge of this structure began its journey toward us, the universe was only about 4 billion years old. The Earth didn't exist. The Sun hadn't formed. The Milky Way was still assembling itself from smaller galaxies. The Hercules-Corona Borealis Great Wall isn't a solid object, of course. Nothing in space at these scales is solid. It's a concentration of gamma-ray bursts, the most energetic explosions in the universe, occurring when massive stars collapse into black holes. These gamma-ray bursts trace the locations of galaxies, and what Horvath's team found was that these galaxies weren't randomly distributed across the sky. They were clustered, organised into an enormous filamentary structure. a cosmic wall of matter stretching across a substantial fraction of the visible universe. But here's the problem that makes this structure impossible. According to the cosmological principle, one of the foundational assumptions of modern cosmology, the universe should be homogeneous and isotropic at large scales. Homogeneous means that matter is distributed uniformly throughout space. No region has significantly more or less density than any other. Isotropic means that the universe looks the same in all directions. There's no preferred orientation or axis in cosmic structure. These assumptions aren't arbitrary. They're based on observations and fundamental physics. Einstein's general relativity, the theory that describes gravity and the large-scale structure of the universe, works most elegantly when the universe is homogeneous and isotropic. The cosmic microwave background radiation, the afterglow of the Big Bang, is remarkably uniform across the entire sky, supporting the idea that the early universe was smooth and evenly distributed. And measurements of galaxy distributions, averaged over sufficiently large volumes, show no significant variations in density. The cosmological principle also imposes a limit on how large structures can be. If the universe is truly homogeneous at large scales, then structures, clusters of galaxies or filaments or walls, should reach a maximum size beyond which the uniformity takes over. Calculations based on cosmic expansion, the finite age of the universe, and the speed of light suggest this maximum size should be around 1.2 billion light-years across. The Hercules-Corona Borealis Great Wall is roughly 8 times larger than this theoretical limit. It shouldn't exist, not because it violates any single law of physics, but because there hasn't been enough time in the universe's history for such a structure to form. Gravity works at the speed of light, and in the 13.8 billion years since the Big Bang, there simply hasn't been sufficient time for gravity to gather matter into structures this large. And yet it exists. We can observe it. We can map its extent. The gamma-ray bursts that trace its structure are real events, occurring in real galaxies, organised in patterns that defy our theoretical expectations. Which brings us naturally to the question of what, exactly, we mean by structure in the universe, and how astronomers came to realise that the cosmos is far more organised than we once believed. If you could step outside the universe and look back at it from some impossible vantage point, you wouldn't see galaxies distributed evenly through space like stars on a uniform background. Instead, you'd see something that looks remarkably like a three-dimensional spiderweb. Vast filaments of galaxies connected at dense nodes, with enormous empty voids between them. Astronomers call this pattern the cosmic web, and it's one of the most striking features of the universe at large scales. This web-like structure wasn't always known. For much of the 20th century, astronomers assumed that galaxies were distributed more or less randomly throughout space. Yes, there were local clusters where galaxies gathered together, like the Virgo cluster or the Coma cluster, but these were thought to be isolated concentrations in an otherwise uniform distribution. The idea that galaxies might be organised into coherent structures spanning hundreds of millions or billions of light-years seemed unlikely. The first hints that the universe had large-scale structure came in the 1980s, when astronomers began conducting extensive redshift surveys, projects to measure the distances to thousands of galaxies and map their three-dimensional positions. One of the most famous early discoveries came in 1989, when Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics published their map of galaxy positions. The map showed something unexpected, a vast sheet of galaxies which they called the Great Wall, stretching across 500 million light-years. This structure, now known as the CFA-2 Great Wall after the center that discovered it, was stunning. It revealed that galaxies weren't scattered randomly, but were organised into enormous flat structures with vast empty regions called voids between them. The voids were as significant as the walls, enormous bubbles of nearly empty space, some spanning 300 million light-years, where galaxies were rare or absent. As redshift surveys expanded, mapping more and more of the sky, the cosmic web became increasingly apparent. Galaxies cluster along filaments, thread-like structures that connect at dense nodes where galaxy clusters form. Between these filaments lie the voids, vast empty regions that contain very little visible matter. The overall pattern resembles foam or the structure of a sponge, with matter concentrated on surfaces and edges while emptiness fills the interior. Understanding why the universe has this structure requires going back to the early universe, shortly after the Big Bang. At that time, matter was distributed almost uniformly but not perfectly. There were tiny density variations, quantum fluctuations from the earliest moments of cosmic inflation that had been stretched to cosmic scales. These variations were small, just 1 part in 100,000 difference in density from place to place, but they were enough. Gravity amplified these small differences. Regions that were slightly denser than average had slightly more gravitational pull, attracting more matter from their surroundings. As matter flowed toward these denser regions, they became denser still, increasing their gravitational attraction further. This positive feedback loop, working over billions of years, gradually transformed the small density fluctuations of the early universe into the cosmic web we observe today. But this process takes time. Gravity works at the speed of light, and matter can only fall together as fast as gravity can pull it. In the 13.8 billion years since the Big Bang, there's been time for structures of a certain size to form, but not time for arbitrarily large structures. The limit, according to our models, should be around 1.2 billion light-years. Beyond that size, the universe simply hasn't existed long enough for gravity to organise matter into coherent structures. And this is where structures like the Hercules-Corona Borealis Great Wall become problematic. They exceed this limit by factors of 5 or 8 or even more. They're structures that, according to our understanding of cosmic evolution, shouldn't have had time to form. Either our theories are wrong, or there's something about the early universe or the nature of structure formation that we don't understand. The cosmic web itself is already a remarkable achievement of cosmological theory and observation. The fact that we can trace how tiny quantum fluctuations in the first fraction of a second after the Big Bang grew into the galaxy-spanning filaments we observe today is a testament to how well we understand cosmic evolution. But these impossibly large structures suggest that understanding isn't complete, that the universe still holds surprises at the larger scales, which leads us to consider what other impossibly large structures have been found, and what patterns, if any, connect them. In June 2021, Alexia Lopez, a PhD student at the University of Central Lancashire, announced the discovery of another structure that challenges our cosmological models. She called it the Giant Arc, a nearly symmetrical arc of galaxies spanning 3.3 billion light-years across the sky. Like the Hercules-Corona Borealis Great Wall, the Giant Arc violates the theoretical size limits for cosmic structures, but what makes it particularly intriguing is its shape and its apparent symmetry. The Giant Arc was discovered using data from the Sloan Digital Sky Survey, one of the most comprehensive maps of the universe ever created. Lopez was studying the distribution of magnesium-2 absorbers, gas clouds that absorb specific wavelengths of light from distant quasars. By mapping where these absorbers appear in the light from thousands of quasars, she could trace the distribution of matter across cosmic distances. What she found was that these absorbers weren't randomly distributed. They formed a coherent arc, a curved structure billions of light-years long. What's particularly striking about the Giant Arc is how complete it appears. It's not a fragment or a partial structure, but a nearly full arc, spanning roughly 1/15 of the entire sky as seen from Earth. If you could somehow see it directly, if your eyes were sensitive to the distribution of galaxies and gas clouds at these distances, some astronomers have suggested that these structures might not be real, that they could be statistical flukes. Random alignments of galaxies that happen to look like coherent structures from our particular vantage point. After all, if you look at a random distribution of points long enough, you'll occasionally find patterns that look organized, even though they arose by chance. The human brain is particularly good at finding patterns, sometimes finding them even where none truly exist. But the statistical analyses conducted on these structures suggest they're real, that the probability of such large concentrations of matter arising by chance alone is extremely low. The Hercules-Corona Borealis Great Wall, for instance, has a statistical significance suggesting it's a genuine structure rather than a random fluctuation. The same applies to the giant arc and many of the other large structures that have been found. So we're left with a puzzle. The universe contains structures that our best theories say shouldn't exist, structures too large to have formed in the age of the universe, structures that violate the cosmological principle's expectation of uniformity at large scales. Either these structures are challenging our understanding of cosmic evolution, or they're telling us something important about the early universe, about the nature of dark matter and dark energy, about how gravity operates at the larger scales. To understand why these structures are so problematic, we need to examine more carefully what the cosmological principle actually says, and why cosmologists believe in it so strongly. The cosmological principle is both an assumption and an observation, a statement about how the universe is organized that has deep philosophical roots and strong empirical support. In its simplest form, it states that the universe is homogeneous and isotropic, that on sufficiently large scales, every region of space looks roughly like every other region, and that there's no special direction or location in the cosmos. This principle has its origins in the Copernican revolution, the realization that Earth isn't the center of the universe. Copernicus showed that Earth orbits the Sun, not the other way around. Later, astronomers showed that the Sun isn't the center of the Milky Way, and that the Milky Way is just one of billions of galaxies scattered through space. Each step moved humanity further from a central privileged position. The cosmological principle extends this to its logical conclusion. Not only is Earth not special, but no location in the universe is special. All places averaged over large enough volumes are equivalent. This might seem like a bold assumption, even an arrogant one. After all, we can only observe the universe from one location, and we can only see a finite portion of it, the observable universe, the region within about 46 billion light-years of us. How can we claim that the entire infinite cosmos is uniform when we can only sample a tiny fraction of it? The answer is that we have strong evidence supporting the cosmological principle, at least within our observable universe. The cosmic microwave background radiation, the light from the Big Bang that has been travelling through space for over 13 billion years, is extraordinarily uniform. Its temperature is the same in all directions to about 1 part in 100,000. This uniformity tells us that the early universe, at least the portion we can observe, was remarkably smooth and homogeneous. Modern galaxy surveys also support homogeneity and isotropy, at least on large scales. When astronomers count galaxies in volumes larger than about 300 million light-years across, they find that the density is roughly constant. There are fluctuations, regions with more or fewer galaxies than average, but these fluctuations average out when you look at large enough volumes. The universe appears statistically uniform. The cosmological principle isn't just philosophically satisfying. It's practically essential for cosmology. Einstein's field equations, the mathematical description of how matter and energy curve space-time and produce gravity, are extraordinarily complex. Solving them for an arbitrary distribution of matter is essentially impossible. But if you assume the universe is homogeneous and isotropic, the equations simplify dramatically. You can solve them exactly, producing the Friedmann equations that describe how the universe expands over time. These Friedmann equations, derived by Alexander Friedmann in the 1920s, form the basis of modern cosmology. They predict that the universe should be expanding, which Edwin Hubble confirmed observationally in 1929. They predict how the expansion rate should change over time depending on the universe's matter and energy content. They predict the existence of the cosmic microwave background and its properties. These predictions have been confirmed so precisely that the cosmological principle and the models built on it seem unassailable. But there's another possibility, one that's both troubling and exciting. It might be that the universe is more structured, more organised, more patterned at large scales than we've assumed. That the homogeneity we expect from the cosmological principle only emerges at even larger scales than we've observed, or that there are processes in the early universe, perhaps related to cosmic inflation or the nature of dark matter, that can create larger structures than we thought possible. To explore these possibilities, we need to understand how structures form in the first place. How tiny quantum fluctuations in the early universe grew into the cosmic web we observe today. The story of cosmic structure begins in the first fraction of a second after the Big Bang, in a period called cosmic inflation. During inflation, the universe expanded exponentially, doubling in size every tiny fraction of time, growing from smaller than an atom to perhaps as large as a grapefruit, or even larger in less than a trillionth of a second. This expansion was driven by a hypothetical energy field called the inflaton field, which dominated the universe's energy density during this brief period. Inflation solved several problems in cosmology. It explained why the universe is so flat, why its geometry is so close to Euclidean rather than curved. It explained why the cosmic microwave background is so uniform, why distant regions that couldn't have been in causal contact appear to have the same temperature. And crucially for our story, it explained where the seeds of cosmic structure came from. During inflation, the inflaton field underwent quantum fluctuations, tiny random variations in its energy density caused by the inherent uncertainty of quantum mechanics. These fluctuations were microscopic, but inflation stretched them to cosmic scales. By the end of inflation, quantum fluctuations that had existed at subatomic scales were suddenly stretched across light years, or even much larger distances. When inflation ended, the energy in the inflaton field converted into ordinary matter and radiation, filling the universe with an intensely hot plasma of particles. The quantum fluctuations from inflation became variations in the density of this plasma, regions that were slightly denser or less dense than average. These density variations were small, just 1 part in 100,000, but they were enough to become the seeds from which all cosmic structure would eventually grow. Gravity amplified these small density variations. Regions that were slightly denser had slightly more mass, which meant slightly stronger gravitational pull. This extra gravity attracted more matter from the surrounding space, making the region denser still. Meanwhile, regions that started slightly less dense than average lost matter to their denser neighbours, becoming increasingly empty. This process, called gravitational instability, is the fundamental mechanism by which structure grows in the universe. But gravitational instability takes time. In the early universe, the matter was too hot and energetic for gravity to win. Radiation pressure, the outward push from intense light and heat, balanced gravity's inward pull. Only after the universe had expanded and cooled sufficiently could matter begin to clump under gravity's influence. And even then, the clumping was gradual, small over-densities growing slowly larger over millions and billions of years. The rate at which structure grows depends on several factors. The universe's expansion rate plays a role. Faster expansion means gravity has less time to pull matter together. The amount and nature of dark matter is crucial. Dark matter, which doesn't interact with light or ordinary matter except through gravity, makes up about 85% of the universe's total matter, and it began clumping earlier than ordinary matter because it wasn't affected by radiation pressure. Computer simulations of structure formation, running the equations of gravity and cosmic expansion forward from initial conditions based on inflation, can reproduce the cosmic web remarkably well. These simulations start with small density fluctuations and watch as gravity amplifies them over billions of years. First, small clumps form. Then these clumps merge into larger structures. Filaments develop where material streams along gravitational channels. Voids grow as matter flows out of underdense regions toward overdense ones. By the present day, simulations produce structures that look strikingly similar to what we observe. A cosmic web of filaments, nodes, and voids. But here's the key point. These simulations predict a maximum size for structures based on how much time gravity has had to work. The universe is 13.8 billion years old. In that time, gravity, working at the speed of light, can only pull matter together across finite distances. Structures can grow from the initial density fluctuations up to a certain size, but not larger. That maximum size, as we've mentioned, is around 1.2 billion light-years. This prediction is robust. It doesn't depend much on the precise values of cosmological parameters or the details of inflation. It's a consequence of the finite age of the universe and the finite speed at which gravity acts. And yet structures larger than this limit exist. They've been observed, mapped, and analysed. Their statistical significance suggests they're real, not artifacts or illusions. This creates a genuine tension in cosmology. Either our understanding of structure formation is incomplete, missing some mechanism that can produce larger structures than we expect, or these observed structures are challenging the cosmological principle itself, suggesting that the universe isn't as homogeneous as we've assumed. Or perhaps both. Perhaps there are insights to be gained from these impossible structures that will deepen our understanding of how the universe evolved from quantum fluctuations to the rich cosmic tapestry we observe today. As we move into our second act, we'll explore what astronomers have learned about the universe's large-scale structure, how they map these cosmic patterns, and what the discovery of increasingly large structures has revealed about the limits of our cosmological models. To find impossibly large structures in the universe, astronomers first need to measure distances to billions of galaxies, determining not just where they appear in the sky, but how far away they are. This three-dimensional mapping is essential for identifying structures like the Hercules-Corona Borealis Great Wall or the Giant Arc. But measuring distances to objects billions of light-years away is one of the great technical challenges in astronomy. The most fundamental method for determining cosmic distances is the redshift. When astronomers observe distant galaxies, they notice that the light from these galaxies is shifted toward longer, redder wavelengths compared to light from nearby galaxies. This redshift occurs because the universe is expanding, stretching space itself and carrying galaxies away from each other. As space stretches, light travelling through it also stretches, increasing in wavelength, shifting from blue toward red. The amount of redshift tells us how much the universe has expanded since the light began its journey. A galaxy with a large redshift is far away, and we're seeing it as it was long ago, when the universe was younger and smaller. A galaxy with small redshift is relatively nearby, and we're seeing it as it was more recently. By measuring redshift, astronomers can determine distance, or more precisely, they can determine what cosmologists call the light travel distance, how far the light has travelled through space to reach us. Measuring redshift itself is relatively straightforward. Astronomers take spectra of galaxies, breaking their light into component wavelengths like a prism creates a rainbow. In these spectra, certain features appear at characteristic wavelengths, emission or absorption lines caused by specific atoms like hydrogen or oxygen. By comparing the observed wavelengths of these features to their laboratory wavelengths, astronomers calculate the redshift. But converting redshift into distance requires knowing the universe's expansion history, how the expansion rate has changed over time. This history depends on the universe's matter and energy content, particularly the amounts of ordinary matter, dark matter, and dark energy. Cosmologists have determined these quantities precisely using observations of the cosmic microwave background, supernovae, and large-scale structure, allowing redshift to be converted into distance with reasonable accuracy. For mapping large-scale structure, astronomers conduct redshift surveys, projects to measure the redshifts of hundreds of thousands or even millions of galaxies. The Sloan Digital Sky Survey, which has been operating since 2000, has measured redshifts for over 4 million objects, creating the most detailed three-dimensional map of the universe ever made. Other surveys, like the 2-degree field galaxy redshift survey and the BOSS survey, have also contributed millions of galaxy distances. These surveys reveal the cosmic web in stunning detail. When plotted in 3 dimensions, with 2 coordinates representing position on the sky and the third representing distance, the galaxies trace out filaments, walls, and voids. You can see sheets of galaxies. Vast surfaces containing thousands of galaxies, separated by empty voids, hundreds of millions of light years across. You can trace filaments connecting dense clusters. The structure is intricate, beautiful, and remarkably consistent with theoretical predictions based on gravitational instability growing from initial quantum fluctuations. But redshift surveys have limitations. They're time-consuming. Measuring spectra for millions of galaxies requires years of telescope time. They're incomplete, covering only fractions of the sky, and they're limited in depth. Even the deepest surveys can only reach so far before galaxies become too faint to observe. This means that the largest structures, those spanning billions of light years, are difficult to map completely. We often see only portions of them, like glimpses of vast cosmic architecture that extends beyond our ability to observe. For detecting the most distant and large structures, astronomers sometimes use tracers, objects that are bright enough to be seen at extreme distances, and whose positions trace the underlying distribution of matter. Gamma-ray bursts, the explosions that trace the Hercules-Corona Borealis Great Wall, are one such tracer. Quasars, extremely bright galactic cores powered by supermassive black holes, are another. By mapping where these bright objects appear, astronomers can infer the distribution of galaxies and matter, even at distances where individual galaxies are too faint to detect. The giant arc, for instance, was discovered not by mapping galaxies directly, but by mapping magnesium-2 absorbers, gas clouds that absorb light from background quasars. The positions of these absorbers trace the locations of galaxies and structure, even when the galaxies themselves are too faint to observe individually. This technique, called absorption line mapping, allows astronomers to detect structure at distances and sizes that would be impossible to map using galaxy positions alone. All of these mapping techniques together have revealed that the universe is richly structured at scales ranging from individual galaxies to billion light-year filaments. But they've also revealed the problematic structures, the ones too large to fit comfortably within our theoretical framework. And as mapping techniques improve, as surveys grow deeper and more complete, more of these impossible structures continue to be found, each one raising new questions about cosmic homogeneity and the limits of structure size. When we look at maps of the cosmic web, we're seeing only the visible matter, the galaxies and gas clouds that emit or absorb light. But this visible matter represents just 15% of the total matter in the universe. The remaining 85% is dark matter, material that doesn't emit, absorb, or reflect light, detectable only through its gravitational effects. And it's dark matter, not ordinary matter, that forms the fundamental framework of cosmic structure. Dark matter was first proposed in the 1930s by Fritz Zwicky, who observed that galaxies and clusters were moving too fast to be held together by the gravity of visible matter alone. The galaxies should have flown apart unless there was additional invisible mass providing extra gravitational binding. Zwicky called this missing mass dark matter, though it would be decades before his idea was widely accepted. The strongest evidence for dark matter came in the 1970s, when Vera Rubin and Kent Ford measured rotation curves of galaxies, plots of how far stars orbit at different distances from the galactic centre. They found that stars in the outer regions of galaxies orbit far faster than expected based on the visible matter. The only explanation was that galaxies are embedded in enormous halos of invisible matter, extending far beyond the visible disk. Today we know that dark matter makes up most of the universe's matter content, and that it played a crucial role in forming cosmic structure. Unlike ordinary matter, dark matter doesn't interact with light or experience radiation pressure. This meant that dark matter could begin clumping under gravity earlier than ordinary matter, forming a skeletal structure into which ordinary matter later flowed. Computer simulations of structure formation include both dark matter and ordinary matter, tracking how each evolves under gravity's influence. These simulations show that dark matter forms a vast network of filaments and halos, a three-dimensional web that pervades all of space. Ordinary matter, attracted by dark matter's gravity, flows into this web, accumulating in the densest regions where dark matter has concentrated. Galaxies form within dark matter halos, and galaxy clusters form where multiple halos merge. The cosmic web we observe, the filaments and walls made of galaxies, is essentially tracing the underlying dark matter distribution. The visible galaxies are like light strung along an invisible framework. We can't see the dark matter directly, but we can infer its presence and distribution from how galaxies organize themselves under its gravitational influence. This relationship between dark matter and visible structure has important implications for understanding large cosmic structures. If structures like the Hercules-Corona Borealis Great Wall exist, then there must be corresponding concentrations of dark matter spanning billions of light years. These dark matter structures would have formed first, providing the gravitational framework into which ordinary matter flowed to create the visible galaxies we observe. Some cosmologists have proposed that the initial density fluctuations from inflation might have been larger at very large scales than we expect. Normally we assume that the density fluctuations from inflation are nearly scale invariant, having similar amplitudes at all scales. But if the fluctuations were somehow enhanced at scales of billions of light years, perhaps due to details of the inflation process we don't understand, then large structures might have formed more easily. Another possibility involves the nature of dark matter itself. Most cosmological models assume dark matter is cold, meaning the particles move slowly compared to the speed of light. Cold dark matter clumps efficiently under gravity, forming structures from small scales upward through hierarchical merging. But if dark matter has properties we haven't accounted for, perhaps interactions between dark matter particles that we've neglected, the structure formation process might behave differently than we expect. There's also the question of whether these large structures are truly coherent, or whether they're chance alignments of smaller structures. The cosmic web is intricate, with filaments connecting and crossing at various scales. What looks like a single 10 billion light-year structure from one perspective might actually be several separate structures that happen to align along our line of sight. Distinguishing genuine large-scale coherence from chance alignment is statistically challenging, but the observations persist. Structures that challenge our models continue to be found, and the tension between theory and observation remains unresolved. Dark matter's role in structure formation is well established, but these impossibly large structures suggest there are still aspects of the process we don't understand, details of dark matter's behaviour, or the early universe's conditions that remain hidden. While much attention focuses on the largest structures in the universe, the filaments and walls where galaxies concentrate, the cosmic web's empty regions are equally remarkable and equally important for understanding large-scale structure. These voids, vast bubbles of nearly empty space, are some of the most distinctive features of the universe at large scales. The largest voids span hundreds of millions of light years and contain very few galaxies. They're not completely empty. They contain some isolated galaxies and dark matter, but their density is far below the cosmic average. Most of the universe's volume is actually in voids, while most of its matter is concentrated in the filaments and walls that surround them. If you were somehow placed randomly in the universe, odds are you'd find yourself in a void, far from any galaxy, surrounded by vast darkness in all directions. Voids form through the same gravitational instability process that creates filaments and clusters. Regions that start slightly less dense than average lose matter to their denser surroundings. As matter flows out toward nearby overdensities, the underdense region becomes increasingly empty, growing into a void. The boundaries of voids, where matter accumulates as it flows outward from the void's interior, often become filaments or walls where galaxies concentrate. The distribution of voids and the structures between them creates a pattern sometimes called the cosmic foam or cosmic sponge. Just as soap bubbles pack together with thin films between them, or as a sponge has solid material surrounding empty spaces, the universe's matter concentrates on surfaces and edges, while voids fill the interior. This pattern is hierarchical. Large voids contain smaller voids, and filaments themselves have structure at smaller scales. One of the best-studied voids is the Buter's void, sometimes called the Great Nothing, discovered in 1981. It spans about 330 million light-years and contains very few galaxies, perhaps just 60, where thousands would be expected based on the average cosmic density. Observations of the Buter's void helped establish that voids are a fundamental feature of cosmic structure, not rare anomalies. The existence of large voids actually supports the cosmological principle in some ways. If the universe were randomly distributed, we'd expect to see some large empty regions just by chance. The fact that voids exist and have predictable properties, based on gravitational instability models, suggests that cosmic structure follows understandable physical laws rather than arbitrary patterns. But voids also contribute to the question of maximum structure size. If coherent structures like walls and filaments can only be so large, then the voids they surround should also have maximum sizes. A void that's too large would indicate structure scales beyond what gravity could have created in the available time. The largest known voids are around 400 million light-years across, which is large but not impossibly so given current models. Interestingly, the study of voids has revealed that they're not entirely empty. They contain dark matter, though at lower density than average. They contain some galaxies, often dwarf galaxies that formed in the void's interior rather than in the dense filaments. And they contain dark energy, the mysterious energy that's causing the universe's expansion to accelerate. In fact, because voids are regions where matter is scarce, dark energy's repulsive effect is particularly noticeable, potentially causing voids to expand faster than expected. The relationship between the largest structures and the largest voids is worth contemplating. If structures like the Hercules-Corona Borealis Great Wall exist, spanning 10 billion light-years, then the voids adjacent to such structures might also be extremely large. The cosmic foam should scale coherently, with the size of bubbles related to the thickness of films between them. Finding an impossibly large wall suggests there might be impossibly large voids nearby, though these would be even harder to detect since voids are defined by the absence of bright tracers like galaxies or gamma-ray bursts. Some cosmologists have suggested that voids might be more important for understanding dark energy than previously thought. Dark energy's properties, its density, and how it affects expansion might manifest differently in voids compared to dense regions. Studying the largest voids could provide tests of dark energy models and constraints on modified gravity theories that attempt to explain cosmic acceleration without invoking mysterious dark energy. The interplay between voids and structures creates a universe that's far more interesting than a smooth, uniform distribution of matter. The cosmic web, with its filaments, walls, clusters, and voids, represents a kind of organized complexity that emerged from simple initial conditions through gravitational instability. It's a structure that's both highly ordered, following predictable patterns, and highly complex, with details at every scale from galaxy clusters down to individual galaxies. And the fact that this structure exists at all, that gravity could organize matter into such intricate patterns in just 13.8 billion years, is itself remarkable. That some structures push beyond expected limits makes the universe even more intriguing, suggesting our understanding, while substantial, is still incomplete. To understand whether observed structures are truly impossible or merely unexpected, cosmologists rely heavily on computer simulations. These simulations start with the conditions of the early universe shortly after the Big Bang, initial density fluctuations from inflation, precisely specified amounts of dark matter, dark energy, and ordinary matter, and the laws of gravity and cosmic expansion. Then they run forward in time, calculating how gravity pulls matter together, and how the universe expands, how structures grow from small perturbations into the cosmic web. The most sophisticated simulations, with names like Millennium Simulation, Illustris, and Eagle, track billions of particles representing both dark and ordinary matter. They resolve structures from galaxy clusters down to individual galaxies, spanning scales from tens of millions of light-years down to tens of thousands. Running these simulations requires some of the world's most powerful supercomputers, with calculations taking months of processing time. The results are stunning. Simulations reproduce the cosmic web in remarkable detail, creating virtual universes that look strikingly similar to what we observe. They produce filaments connecting at dense nodes. They create walls and sheets where galaxies concentrate. They form voids of the right sizes and shapes. When astronomers compare simulated galaxy distributions to actual observations, the agreement is impressive, a testament to how well we understand cosmic structure formation at most scales. But here's what's crucial. These same simulations that successfully reproduce the cosmic web also predict maximum structure sizes consistent with theoretical calculations. When researchers analyze the simulated universes, measuring the sizes of the largest coherent structures, they find limits around 1 to 1.5 billion light-years, similar to theoretical expectations. Structures larger than this emerge only as statistical flukes, rare outliers that shouldn't be common. This creates a puzzle. Our simulations, based on well-tested physics and matched to observations at most scales, predict that structures like the Hercules-Corona Borealis Great Wall should be extraordinarily rare, perhaps unique in the entire observable universe. Yet we found multiple such structures: the Giant Arc, the Sloan Great Wall, the Giant GRB Ring, others. Either we're incredibly unlucky, observing a universe that happens to have more large structures than typical, or there's something wrong with the models. One possibility is that the simulations, despite their sophistication, are missing important physics. Perhaps there are processes in the early universe that aren't included in standard models. Cosmic inflation, while explaining the origin of initial density fluctuations, has many possible variants, and different inflation models can produce different patterns of fluctuations. If the actual inflation that occurred in our universe had properties that enhanced large-scale fluctuations, that might explain the large structures we observe. Another possibility involves dark matter. Standard simulations assume dark matter is purely collisionless, interacting only through gravity. But if dark matter has additional interactions, perhaps very weak forces between dark matter particles, structure formation might proceed differently. These interactions could affect how dark matter clumps, potentially allowing larger structures to form more easily or persist more stably. The ongoing development of larger, more detailed simulations continues to test our understanding. As computational power increases, simulations can include more particles, resolve smaller scales, incorporate more detailed physics, and explore larger volumes of space. Some recent simulations have focused specifically on rare events and large-scale structure, asking whether standard models might occasionally produce very large structures even if such structures are improbable. These investigations suggest that standard cosmology can produce structures somewhat larger than the naive theoretical limit under special conditions. But reaching 10 billion light-years remains difficult. It requires specific combinations of initial conditions and evolutionary histories that should be extremely rare. The fact that we observe multiple such structures suggests either that they're not as rare as simulations predict, or that our observable universe is somehow unusual compared to the larger cosmos beyond our observational horizon. This interplay between simulation and observation is how cosmology advances. Models make predictions, observations test them, and discrepancies drive refinement of both observations and theories. The larger structures represent such a discrepancy, a place where observations and standard models don't quite agree, and resolving this tension will likely require new insights into cosmic structure formation. There's a fundamental limit to how much of the universe we can observe, not because of telescope limitations, but because of the finite speed of light and the finite age of the universe. Light from very distant regions hasn't had time to reach us yet, meaning there are portions of the universe that are, in principle, unobservable. This boundary is called the cosmological horizon, or the edge of the observable universe, and it plays a crucial role in thinking about large-scale structure. The observable universe is roughly 46 billion light-years in radius, which seems odd since the universe is only 13.8 billion years old. Shouldn't light have travelled only 13.8 billion light-years? The answer lies in cosmic expansion. While light has been travelling for 13.8 billion years, the space through which it travelled was expanding during that time. The objects that emitted the light we see today were much closer when they emitted it, but expansion has carried them to much greater distances since then. This observable universe contains roughly 2 trillion galaxies, though that number is uncertain. It contains all the structure we can possibly observe, all the galaxies, clusters, filaments, walls and voids within our cosmological horizon. Beyond this boundary, the universe continues, perhaps infinitely, but we can never observe it. Light from beyond the horizon hasn't had time to reach us and never will, because cosmic expansion is accelerating, carrying distant regions away faster than light can traverse the growing space. Now here's an interesting question. What if structures like the Hercules-Corona Borealis Great Wall extend beyond our observable horizon? What if what we're seeing is just a portion of an even larger structure that continues beyond the edge of what we can observe? If this were true, we'd be dramatically underestimating these structures' true sizes. This possibility is difficult to test directly since we can't observe beyond the horizon, but we can ask whether the largest observed structures show signs of extending beyond our measurement boundaries. Do they have sharp edges, suggesting they terminate within observable space? Or do they fade gradually at the edges of our surveys, suggesting they might continue beyond where we can see? For most large structures, the edges are poorly defined because our surveys are incomplete and the structures themselves are irregular. The Hercules-Corona Borealis Great Wall, traced by gamma-ray bursts, doesn't have sharp boundaries. The giant arc similarly fades at its edges where the survey data becomes sparse. This ambiguity means we can't definitively say whether these structures are complete within observable space or whether they continue beyond our observational limits. Some cosmologists have suggested that studying structures near the edge of observability might reveal whether the cosmological principle holds at very large scales. If we see structures consistently throughout our observable universe, with no systematic changes as we look to greater distances, that supports homogeneity. But if the largest structures are preferentially found at certain distances or directions, that might suggest violations of homogeneity or isotropy. Current observations don't show clear violations of the cosmological principle in this sense. The universe looks statistically similar in all directions and at all observable distances once you average over large enough scales. But the presence of individually large structures creates tension with this statistical homogeneity. The structures are rare enough that they don't violate average uniformity, but they're large enough that their existence seems problematic given theoretical expectations. There's also the question of what exists beyond the observable universe. If the universe is infinite, as some models suggest, then there are infinitely many regions like our observable universe, each with its own structures and galaxies. In such an infinite cosmos, any finite structure size, no matter how large, would appear somewhere. We might simply happen to live in a region with unusually large structures, but this explanation feels unsatisfying. It essentially appeals to chance, saying we got unlucky in a way that creates tension with our theories. While possible, it doesn't advance our understanding. The goal of cosmology is to explain what we observe using physical principles, not to attribute observations to luck. As we move into the third act of our journey, we'll explore what these large structures might be telling us about the universe's fundamental nature, about dark energy and cosmic expansion, about the limits of our current cosmological models, and where new physics might be needed to explain what we observe in the vast darkness between galaxies. In 1998, two independent teams of astronomers studying distant supernovae announced a discovery that would revolutionize cosmology and earn them the Nobel Prize. They found that the universe's expansion is accelerating, speeding up rather than slowing down. This acceleration was completely unexpected. Gravity should cause expansion to slow over time, yet somehow the universe was doing the opposite. The explanation cosmologists settled on was dark energy, a mysterious form of energy that fills all of space and exerts a kind of negative pressure, pushing space apart rather than pulling it together. Dark energy makes up about 70% of the universe's total energy content, far more than either dark matter or ordinary matter. Yet its nature remains one of the deepest mysteries in physics. Dark energy's effect on cosmic expansion is well measured. It causes the expansion rate to increase over time, which has profound implications for the universe's future. But dark energy also affects structure formation, and this connection might be relevant to understanding the largest cosmic structures. In the early universe, dark energy was negligible. Matter and radiation dominated the energy density, and cosmic expansion was decelerating as expected. During this matter-dominated era, structure grew efficiently. Gravity could pull matter together into increasingly large structures without competition from dark energy's repulsive effect. But as the universe expanded, matter became more diluted while dark energy remained constant. Eventually, about 5 billion years ago, dark energy began dominating the expansion. Once this happened, cosmic expansion started accelerating, and structure growth slowed. Gravitational instability still operates. Galaxies still form and merge, but the process is less efficient than it was in the matter-dominated era. This transition from matter domination to dark energy domination represents a boundary in structure formation. Structures that formed before this transition could grow large because they had sufficient time in a favourable environment. Structures attempting to form after the transition face stronger competition from cosmic acceleration and grow more slowly. The larger structures we observe, like the Hercules-Corona Borealis Great Wall, must have started forming in the matter-dominated era. Their immense size suggests they began as very large density fluctuations that gravity then amplified over billions of years. But here's the puzzle. Even in the matter-dominated era, when conditions were most favourable for structure growth, there should still be limits on how large structures can become. Dark energy's eventual dominance doesn't help explain structures that are already larger than expected. If dark energy was slightly weaker in some regions or slightly stronger in others, this could affect how structures grow. Regions with weaker dark energy would have slower expansion and might form larger structures more easily. Regions with stronger dark energy would have faster expansion and might form structures less efficiently. Observing whether the larger structures correlate with any measurable variations in cosmic expansion could test whether dark energy varies spatially. Current observations don't show clear evidence for dark energy variations. But the measurements are difficult. Dark energy's effects are only significant at the largest scales and longest timescales, precisely where observations are most challenging. The cosmic microwave background provides some constraints, showing that dark energy was negligible in the early universe. Supernovae at various distances show consistent acceleration, suggesting dark energy's density hasn't changed much over cosmic time. But there's still room for subtle variations or unexpected behaviour. Some modified gravity theories, which attempt to explain cosmic acceleration without invoking mysterious dark energy, predict different structure formation histories than standard models. These theories might allow larger structures to form or persist differently than in standard cosmology. Testing these alternatives requires comparing observed structures to detailed predictions. Do the larger structures we observe have properties, sizes, shapes, distributions that match what standard dark energy models predict? Or do they require modifications to our cosmological framework? The presence of apparently impossibly large structures suggests tension with standard models, but determining whether this tension requires new physics or just better understanding of standard physics remains an open question. Dark energy represents one of the great unknowns in modern physics. We know it exists, in the sense that we observe its effects on cosmic expansion. We know roughly how much there is, about 70% of the universe's energy. But we don't know what it is, what causes it, or whether it's truly constant in time and space. The largest cosmic structures might provide clues about dark energy's nature, subtle hints that could guide us toward understanding this mysterious component that dominates our universe. To understand why certain structures might be unexpectedly large, we need to return to the very beginning, to the first tiny fraction of a second after the Big Bang when cosmic inflation occurred. This brief period of exponential expansion is responsible for creating the initial density fluctuations that eventually grew into all cosmic structure, and the detailed properties of inflation might hold the key to understanding the larger structures. Inflation was proposed in the 1980s by Alan Guth and others to solve several problems in cosmology. Why is the universe so flat? Why is it so uniform? Why don't we see magnetic monopoles or other exotic particles that should have been created in the very early universe? Inflation answered all these questions elegantly by proposing that the universe underwent an extraordinarily rapid expansion phase, during which it grew by a factor of at least 10 to the 26th power. From smaller than an atom to potentially larger than our current observable universe. This measured spectral index has important implications for structure formation. It tells us that the initial seeds for the larger structures were slightly weaker than seeds for smaller structures. This means large structures should have grown slightly less efficiently than small structures, making it even more difficult to explain structures as large as the Hercules-Corona Borealis Great Wall. But here's where things get interesting. The spectral index is measured reliably only at scales probed by cosmic microwave background observations, roughly from the size of galaxy clusters down to smaller scales. At much larger scales beyond what the microwave background can probe, the behavior of density fluctuations is less certain. Different inflation models make different predictions about what happens at these very large scales. Some models predict that the spectral index might change at large scales, that fluctuations at scales of billions of light years might be stronger than expected based on extrapolating from smaller scales. If this were true, it would mean the seeds for very large structures were stronger than we've assumed, making it easier for such structures to form. Other models suggest inflation might have left behind features, specific scales where fluctuations are enhanced or suppressed, that wouldn't be visible in the cosmic microwave background but might affect structure at larger scales. These features could arise from transitions in the inflaton field's behavior or interactions with other fields during inflation. Testing these ideas is difficult because we can't observe the universe at scales much larger than our observable horizon. We're limited to studying structures within our cosmic neighbourhood, and while that neighbourhood is vast by human standards, it's just a tiny fraction of the total universe. If inflation's behaviour at very large scales differs from what we expect, we might never be able to verify it directly. But there's an indirect way to test inflation models using the largest observed structures. If these structures require stronger initial fluctuations at large scales than standard models predict, that would favour inflation models with spectral features or non-standard behaviour. Conversely, if standard inflation predictions can accommodate the observed structures with reasonable probability, that supports simpler inflation models. Current analyses suggest tension, but not outright contradiction. The larger structures are at the edge of what standard inflation models can produce. requiring somewhat unlikely initial conditions but not impossible ones. Whether this tension is significant enough to require new inflation physics, or whether it's just telling us that we observe a slightly unusual region of the universe remains debatable. There's also the question of how inflation ended. The transition from exponential expansion to normal expansion is called reheating, when the inflaton field's energy converted into ordinary particles and radiation. The details of reheating might affect the density fluctuation spectrum, potentially enhancing certain scales or creating features that would impact large-scale structure formation. Inflation remains one of the most successful theories in cosmology, explaining the universe's large-scale uniformity and flat geometry, while providing a mechanism for generating the density fluctuations we observe. But it's also one of the least understood at a fundamental level. We don't know what the inflaton field really is, what potential energy it has, or how it connects to other physics. The largest cosmic structures might be providing hints about these deep questions, whispering secrets about the universe's first moments when everything we observe was smaller than a subatomic particle. Einstein's general relativity has been tested extensively and has passed every test with remarkable precision. From Mercury's orbital precession to gravitational waves from colliding black holes, general relativity's predictions match observations spectacularly well. Yet some physicists wonder whether general relativity might be incomplete at the larger scales, whether modifications to gravity could explain both cosmic acceleration and the unexpectedly large structures we observe. The motivation for considering modified gravity comes partly from dark energy and dark matter. Both are invisible, known only through gravitational effects. Dark energy in particular seems suspiciously fine-tuned. Its density is about 120 orders of magnitude smaller than naive quantum field theory predictions, yet it's perfectly suited to causing the observed cosmic acceleration. This fine-tuning problem makes some physicists wonder whether dark energy isn't a real substance, but rather a symptom of gravity behaving differently at cosmic scales than Einstein predicted. Various modified gravity theories have been proposed. Some suggest that gravity becomes weaker at very large distances, reducing the universe's expansion-deceleration and mimicking dark energy's effects without requiring any mysterious energy component. Others propose additional dimensions beyond our familiar 3 spatial dimensions, with gravity leaking into these extra dimensions at large scales, again producing effects that look like dark energy. For our purposes, the interesting question is whether modified gravity could affect structure formation in ways that allow larger structures than standard gravity predicts. If gravity behaved differently at scales of billions of light years, perhaps being stronger or operating more efficiently, then structures larger than expected might form more easily. Some FFR models predict enhanced structure formation at large scales, allowing larger structures to grow than would be possible in standard gravity. This happens because the modified gravity equations have additional degrees of freedom that can source density fluctuations beyond what matter alone provides. Whether any FFR model can simultaneously explain both cosmic acceleration and the largest observed structures while still matching all other observations remains an active research question. Another approach involves theories with extra fields beyond the standard gravitational field. These scalar tensor theories include an additional scalar field that couples to matter and affects how gravity operates. Depending on the scalar field's properties, these theories can produce various effects on cosmic expansion and structure formation. Testing modified gravity theories against observations is challenging because these theories must match general relativity's predictions in regimes where Einstein's theory is well tested, while producing different behaviour only at scales or in situations where tests are difficult. The solar system provides extremely precise tests of gravity, and any modified theory must reduce to general relativity in this regime. Galaxy-scale gravitational lensing provides additional constraints. Modified gravity theories must navigate these constraints while still providing explanatory power for cosmic phenomena. The larger structures potentially provide a test of modified gravity. If standard general relativity truly limits structure sizes to around 1.2 billion light-years, then observing significantly larger structures might favour modifications. But this test requires careful statistical analysis. How many large structures would we expect to see by chance in standard gravity? How much more common would they be in modified gravity? Are the observed structures truly problematic for standard models, or merely somewhat unlikely? Current analyses suggest that while the larger structures are at the edge of standard model predictions, they're not so extreme that they definitively require new gravity. Modified gravity might make them more likely, but it's not clear that they're impossible without modification. This ambiguity means modified gravity remains an interesting possibility, but not yet a necessity. There's also philosophical resistance to modifying general relativity without compelling reason. Einstein's theory is elegant and successful, and modification should not be undertaken lightly. Before accepting that gravity needs modification at large scales, cosmologists want to exhaust other possibilities. Better understanding of structure formation within standard models, improved statistical analyses of observations, consideration of observational selection effects that might make large structures seem more common than they are. Yet the possibility remains intriguing. General relativity was formulated and tested primarily at solar system and galactic scales. Applying it to the entire universe, to scales billions of light-years across where space-time curvature is extremely weak, but integrated over vast distances, represents an enormous extrapolation. It would not be surprising if subtle corrections or modifications became necessary at these extreme scales. The largest cosmic structures thus serve as laboratories for testing gravity in regimes far from everyday experience. They're not definitive evidence against Einstein's theory, but they're intriguing hints that our understanding might be incomplete, that the universe might have surprises waiting at its larger scales. One possible explanation for why our observable universe contains structures that seem improbably large is that we're simply observing an unusual region. If the universe is vastly larger than our observable portion, perhaps infinitely large, then somewhere among all possible regions there would be some with unusually large structures. We might happen to live in such a region. This explanation invokes what philosophers call the anthropic principle or observer selection effects. The idea is that not all regions of the universe are equally likely to be observed, because observers can only exist in regions with suitable properties. If intelligent life requires certain conditions, then we necessarily find ourselves in a region that meets those conditions, regardless of how typical such regions are. Applied to large structures, the argument would be that most regions of the universe have typical structure distributions matching cosmological models, but some regions happen to have unusually large structures through statistical fluctuation. We observe one of these unusual regions not because unusual regions are common, but simply because we happen to find ourselves in one. This explanation is difficult to test directly. We can't observe regions of the universe beyond our cosmological horizon, so we can't verify whether other regions have more typical structure distributions. We're stuck with observing only our local neighbourhood and trying to infer whether it's representative of the whole. But the anthropic argument seems unsatisfying for this particular question. Unlike fine-tuning of physical constants, where anthropic reasoning might explain why we observe constants suitable for life, there's no obvious reason why large cosmic structures would be necessary for or conducive to intelligent observers. The existence of galaxies, stars and planets might depend on overall matter density and force strengths, but whether those galaxies organize into 10 billion light-year walls seems irrelevant to life's possibility. So while we might happen to live in an unusual region, there's no anthropic reason that would make unusual regions more likely to be observed. This weakens the anthropic explanation compared to cases where observable properties genuinely affect observer existence. The question of whether our observable universe is typical connects to deeper questions about the nature of cosmic inflation and whether it produces a multiverse. Some versions of inflation theory, called eternal inflation, predict that inflation never completely ends. In some regions, inflation stops and normal expansion begins, creating bubbles or pockets of post-inflationary space. But in other regions, inflation continues, and these regions themselves spawn more pockets where inflation ends. In eternal inflation, the universe becomes a vast collection of separate regions, each with potentially different properties. The laws of physics might be the same everywhere, or they might vary if different regions settle into different vacuum states with different particle physics. This multiverse scenario provides a natural explanation for fine-tuning. If every possible outcome occurs somewhere in the multiverse, observers necessarily find themselves in regions where conditions support life. But even in multiverse scenarios, the question of structure sizes remains. Unless there's physical variation between regions that affect structure formation, presumably all regions would have similar structure distributions. The larger structures would be similarly unlikely everywhere. So observing unusually large structures wouldn't favour multiverse scenarios, specifically unless those scenarios predicted physical variations that affect structure formation. There's also the question of what typical means in an infinite universe. If the universe is infinite, then every finite structure, no matter how large, exists infinitely many times. There are infinitely many regions with only small structures, infinitely many with medium structures, and infinitely many with very large structures. In what sense is one kind of region more typical than another, if all kinds occur infinitely often? This question touches on deep issues in probability theory and cosmology. How do we define probabilities in infinite universes? If everything possible happens infinitely many times, how do we calculate how likely it is that we observe what we do? Cosmologists have developed sophisticated approaches to these questions, but they remain philosophically subtle. For our purposes, the relevant point is that while multiverse or anthropic explanations for the larger structures are possible, they're not particularly satisfying. They essentially concede that we can't explain why our observable universe has the properties it does, appealing instead to luck or selection effects. This might ultimately be correct, but before accepting it, cosmologists prefer to explore whether better understanding within standard single-universe models can explain observations. The larger structures thus challenge us to think carefully about what we can and cannot explain, about the role of chance in cosmic observations, and about whether our observable universe is representative of a larger cosmos beyond our horizon. As we reach the midpoint of our journey, having explored the larger structures in the universe, the theories that struggle to explain them, and the various possibilities for resolving the tension, it's worth pausing to reflect on what these discoveries mean more broadly. The existence of structures like the Hercules-Corona Borealis Great Wall represents a kind of cosmic humility lesson. Despite our remarkable progress in understanding the universe, despite our ability to trace cosmic history from the Big Bang to the present, despite our success in predicting the cosmic microwave background and explaining cosmic expansion, the universe still surprises us. It still contains phenomena we struggle to fully explain, patterns that challenge our best theories. This is as it should be. Science advances through the interplay between theory and observation, between prediction and surprise. If observations always perfectly match predictions, we'd learn nothing new. It's precisely when observations challenge theories that science makes progress, forcing us to refine our models, reconsider assumptions, and sometimes develop entirely new frameworks. The largest cosmic structures sit in an interesting middle ground. They're not completely inexplicable, not violations of known physics so severe that they overturn our entire cosmological framework. We can imagine several possible explanations: variations in dark energy, subtleties in inflation, modified gravity, statistical fluctuations in an infinite universe. Each of these possibilities is physically plausible and worth exploring. But they're also not comfortably explained by standard models. They push boundaries, creating tension that suggests something in our understanding needs adjustment. Whether that adjustment will be major, a fundamental revision of cosmological principles, or minor, a refinement of details within existing frameworks, remains to be seen. This state of productive tension is common in science. For decades, the measured rotation curves of galaxies didn't match predictions based on visible matter. This tension eventually led to the dark matter hypothesis, which has become a pillar of modern cosmology, despite dark matter never being directly detected. For years, supernova observations showed cosmic expansion behavior that didn't match expectations, leading to the dark energy hypothesis that now dominates cosmological models. In both cases, observations that didn't fit theories eventually prompted major conceptual advances. Will the larger structures lead to similar breakthroughs? It's too early to say. Perhaps future observations will show these structures are less unusual than they currently appear. Perhaps improved simulations will demonstrate that standard models can produce such structures more easily than we thought. Or perhaps these structures really are pointing toward new physics, hinting at modifications to our cosmological framework that future generations will recognize as crucial. There's also a kind of aesthetic quality to these larger structures, a grandeur that captures imagination even beyond their scientific significance. 10 billion light-years across, a structure so vast that light takes longer to cross it than Earth has existed, a pattern in galaxy distribution that spans a significant fraction of the observable universe. These aren't just data points or statistical anomalies, they're cosmic architecture on the most magnificent scale imaginable. They remind us that the universe is not just a collection of particles following equations, though it is that. It's also organised, structured, patterned in ways we're only beginning to understand. The cosmic web, with its filaments and voids, isn't random chaos. It's a kind of order that emerged from simple initial conditions through the working of gravity over cosmic time. And the larger structures represent the extreme end of that order, the places where cosmic organisation reaches its maximum extent. Contemplating these structures also puts human scale in perspective. We inhabit a planet 8,000 miles in diameter, orbiting a star in a galaxy 100,000 light-years across. That galaxy is separated from the nearest major galaxy by 2.5 million light-years. And that entire local group is utterly dwarfed by structures billions of light-years in extent. Structures so large that our entire visible sky would show only a small portion of them if we could somehow see their full extent. Yet despite this vast difference in scale, we can understand these structures, at least partially. We can observe them, measure them, build theoretical models of how they formed. The same physical laws that govern falling apples on Earth govern the growth of billion light-year filaments in space. There's a unity to physics, a universality that lets us use human minds and human-built instruments to comprehend the largest structures in existence. This ability to understand the universe, to find patterns and formulate laws that describe cosmic phenomena, is itself remarkable and perhaps mysterious. Why should the universe be comprehensible? Why should mathematical theories developed by humans explain galaxies and structure formation? These are deep questions that philosophers and physicists continue to ponder. For now, as we prepare to move into our fourth act, we'll continue exploring what the larger structures teach us, looking more closely at specific structures and what makes each unique and challenging to explain. Before the Hercules-Corona Borealis Great Wall, before the Giant Arc, there was the Sloan Great Wall, discovered in 2003 by J. Richard Gott and Mario Urich, while analysing data from the Sloan Digital Sky Survey. At the time of its discovery, it was the largest known structure in the universe, spanning 1.37 billion light-years, and it represented the first clear challenge to cosmological expectations about maximum structure sizes. The Sloan Great Wall is a vast filament of galaxies located roughly 1 billion light-years from Earth in the direction of the constellations Ursa Major, Leo and Draco. It contains thousands of galaxies arranged in a long, somewhat irregular filament, with several dense knots where galaxy clusters are formed. The structure was identified by mapping the three-dimensional positions of galaxies from the Sloan survey and looking for regions of enhanced density. What made the Sloan Great Wall significant wasn't just its size, but what it revealed about the cosmic web's complexity. Previous large structures, like the CFA2 Great Wall discovered in 1989, were already pushing theoretical boundaries at 500 million light-years. The Sloan Great Wall was nearly 3 times larger, definitively exceeding the expected homogeneity scale of about 300 to 400 million light-years that was commonly cited at the time. The discovery sparked a debate about what constitutes a single structure. Is the Sloan Great Wall truly one coherent entity that formed through gravitational collapse from a single, large-scale density fluctuation? Or is it several separate structures that happen to align from our viewing perspective? This question of structural coherence would become central to evaluating all subsequent large structure discoveries. Researchers address this question through statistical analysis, calculating whether the galaxy overdensity in the Sloan Great Wall region could arise by chance from a random distribution, or whether it represented genuine large-scale structure. They also looked at galaxy motions, peculiar velocities caused by gravitational attraction, to determine whether galaxies in different parts of the structure showed correlated motions suggesting they formed together. The analyses supported the view that the Sloan Great Wall is a genuine large-scale structure rather than a chance alignment. The statistical significance was strong enough to conclude that this wasn't just pattern recognition, finding structure in randomness. Galaxies in the wall showed spatial correlations consistent with formation from a common large-scale density fluctuation. But the Sloan Great Wall's size remained problematic for theoretical models. Simulations based on standard cosmology with measured amounts of dark matter and dark energy struggled to produce structures this large with any significant frequency. The wall was at the extreme tail of the distribution of structure sizes, possible but unlikely. Its existence didn't overturn cosmological models but created tension, suggesting either that our observable universe was somewhat unusual or that structure formation processes weren't completely understood. The Sloan Great Wall also revealed the cosmic web's richness in the local universe. Within this vast filament, astronomers could identify hundreds of individual galaxy clusters and groups, each itself a significant structure. The wall wasn't uniformly dense but had a hierarchy of structure, denser knots connected by thinner filaments, with smaller voids scattered throughout. This hierarchical nature is characteristic of structure formation through gravitational instability, where smaller structures form first and then merge into larger ones. Studying the Sloan Great Wall in detail provided insights into how the cosmic web evolves. By mapping the distribution of galaxies, their masses, their star formation rates and other properties, astronomers could test models of how galaxies form and evolve within large-scale structure. Galaxies in dense clusters evolve differently than galaxies in sparse filaments, and the Sloan Great Wall provided examples of both environments within a single large structure. The discovery also spurred interest in searching for other large structures. If the Sloan Great Wall existed and was barely within theoretical limits, might there be even larger structures waiting to be found? This question motivated deeper surveys and more systematic searches for large-scale structure, eventually leading to the discoveries of the giant GRB ring, the giant arc, and ultimately the Hercules-Corona Borealis Great Wall. Looking back now, the Sloan Great Wall seems almost modest compared to these later discoveries. At 1.37 billion light-years, it's actually close to the theoretical homogeneity scale, well below the size of the Hercules-Corona Borealis Great Wall. But its discovery was pioneering, establishing methods for identifying and analysing large structures and demonstrating that the universe contained structures at the edge of what theory predicted. It opened the door to the realisation that cosmic structure might extend further than anyone had expected. In 2015, astronomers led by Lajos Balaz announced the discovery of an extraordinary structure, a ring-shaped arrangement of 9 gamma-ray bursts spanning about 5 billion light-years across the sky. They called it the giant GRB ring, and if confirmed as a genuine coherent structure, it would be one of the largest and most unusual structures ever observed. Gamma-ray bursts are among the most energetic events in the universe. Brief flashes of intense gamma radiation lasting from milliseconds to several minutes. They're caused by stellar explosions, either massive stars collapsing into black holes, or pairs of neutron stars or black holes merging. Because they're so bright, gamma-ray bursts can be seen at enormous distances, making them useful tracers of large-scale structure. The giant GRB ring consists of 9 gamma-ray bursts that all occurred at roughly the same distance from Earth, about 7 billion light-years away. Their positions on the sky aren't random, but form a roughly circular or arc-shaped pattern spanning about 70 degrees of sky. The structure was identified by analysing the three-dimensional distribution of all known gamma-ray bursts and looking for statistically significant clustering patterns. What makes the giant GRB ring particularly intriguing is its geometry. Unlike filaments or walls, which are common features of the cosmic web, rings are unusual. The cosmic web typically has filaments connecting at nodes with voids between them, not large ring-shaped structures. If the giant GRB ring is a genuine physical structure rather than a chance alignment, it would require explanation for why matter organised into this particular geometry. Some researchers have suggested the ring might trace the edge of an enormous void, a vast bubble of nearly empty space with galaxies concentrated on its boundary. Voids can have galaxies accumulating on their edges where matter flowed outward from the void's interior and collected at the boundary with denser regions beyond. If such a void were sufficiently large and we viewed it from an appropriate angle, we might see its edge as a ring-shaped distribution of galaxies. But explaining a 5 billion light-year void presents its own challenges. Voids grow over time as matter flows out of underdense regions. But there are limits to how large they can grow in the universe's finite age. The largest well-studied voids are 300 to 400 million light-years across. A void billions of light-years across would require exceptional initial conditions or new physics and structure formation. The statistical significance of the giant GRB ring has been debated. Some analyses suggest the probability of 9 gamma-ray bursts arranging themselves in such a pattern by chance is extremely low, less than 1 in 20,000. This would make the ring a genuine structure with high confidence. Other analyses are more cautious, noting that when you look for patterns in large data sets, rare coincidences become more likely, and the apparent significance might be reduced once you account for this look elsewhere effect. The debate highlights a general challenge in identifying large structures, defining clear criteria for what constitutes a structure, and then calculating probabilities fairly. If you look at all possible ways of grouping objects and all possible geometric patterns, you'll eventually find something that looks significant. Determining whether a pattern is genuinely meaningful or a statistical artifact requires careful analysis. For the giant GRB ring, the geometry is striking enough that many researchers believe it represents a genuine structure. 9 gamma-ray bursts at similar distances forming a coherent pattern seems unlikely to be chance. But understanding what physical structure the gamma-ray bursts are tracing remains uncertain. Are they marking a giant ring of galaxies, the edge of a vast void, several unrelated structures that happen to align? The giant GRB ring also raises questions about whether other similar structures exist. If one ring-shaped structure of this size exists, are there others? Have we simply not searched carefully enough? Or is the giant GRB ring truly unique in the observable universe? The rarity of gamma-ray bursts makes this question difficult to answer. We've detected only thousands of gamma-ray bursts total, far fewer than the millions of galaxies mapped by surveys like Sloan. With limited sampling, finding patterns becomes statistically challenging. The discovery method for the giant GRB ring, using gamma-ray bursts as tracers, represents an innovative approach to mapping large-scale structure. Traditional methods rely on mapping galaxies directly through optical or infrared telescopes, but galaxies become faint at large distances, limiting how far we can map structure. Gamma-ray bursts, being extraordinarily luminous, can be seen at much greater distances, potentially allowing detection of structures too distant for galaxy surveys. This method has limitations, of course. Gamma-ray bursts are rare and randomly distributed in time, so we must wait years or decades to build up sufficient samples. Their positions tell us about structure, but we learn less about the detailed properties of galaxies in those structures. And interpreting what gamma-ray burst distributions tell us about underlying matter requires assumptions about how gamma-ray burst host galaxies trace dark matter and large-scale structure. Despite these challenges, the giant GRB ring remains one of the most intriguing large structure discoveries. Whether it represents a genuine 5 billion light-year ring or several smaller structures, it pushes against theoretical limits and invites deeper investigation into how the larger structures form and what their existence tells us about cosmic evolution. The giant arc, discovered by Alexia Lopez in 2021, represents one of the most recent and intriguing additions to the catalogue of impossibly large structures. Spanning 3.3 billion light-years and displaying remarkable symmetry, it challenges cosmological principles in ways that are still being evaluated by the scientific community. Unlike the Hercules-Corona Borealis Great Wall or the giant GRB ring, which were discovered through gamma-ray bursts, the giant arc was identified using a different technique. Lopez studied magnesium-2 absorption systems, clouds of gas that absorb specific wavelengths of light from background quasars. When light from distant quasars passes through these gas clouds, magnesium atoms absorb light at characteristic wavelengths, leaving dark lines in the quasar's spectrum. By mapping where these absorption systems appear along lines of sight to many quasars, Lopez could trace the three-dimensional distribution of gas, which in turn traces the distribution of galaxies and large-scale structure. What she found was a concentration of absorption systems forming a nearly complete arc across the sky, spanning about 15 degrees, which at the structure's distance translates to about 3.3 billion light-years. The arc's symmetry is striking. It's not a ragged, irregular filament, but a smooth, curved structure with coherent geometry. This symmetry raises questions about how such a regular pattern could form from gravitational instability, which typically produces irregular, clumpy structures. While the cosmic web has overall organization with filaments and voids, individual structures are usually asymmetric, shaped by random fluctuations and the details of mergers and accretion over cosmic time. Lopez and her colleagues calculated the statistical probability of such a structure arising by chance from a uniform distribution. Their analysis suggested the giant arc is a genuine structure with high confidence, unlikely to be a random alignment of unrelated features. The structure's size exceeds the theoretical homogeneity scale by factors of several, placing it firmly in the category of problematic structures that challenge standard cosmological models. What makes the giant arc particularly interesting is its location in the sky. It's found in the same general region as the giant GRB ring, though at a different distance. The two structures appear to be aligned, both forming large arcs or rings in similar directions on the sky. This apparent alignment might be coincidental, but it might also suggest even larger patterns, structures or features that extend across multiple redshift shells and appear as separate arcs at different distances. Some researchers have speculated about whether these aligned structures might be tracing baryon acoustic oscillations at extremely large scales. Baryon acoustic oscillations are density fluctuations imprinted in matter distribution by sound waves in the early universe's plasma before recombination. These oscillations create a preferred scale in matter distribution, about 500 million light-years, that appears as a subtle pattern in galaxy clustering. But the giant arc and giant GRB ring are too large to be explained by standard baryon acoustic oscillations. If they're related to acoustic phenomena at all, it would require mechanisms beyond standard theory, perhaps related to inflation or new physics in the very early universe. This possibility remains speculative but illustrates how these large structures invite creative thinking about cosmic origins. The giant arc also highlights how new discovery methods continue revealing unexpected structures. The use of absorption systems to map structure is relatively new compared to traditional galaxy surveys. As this technique is applied to larger data sets from ongoing quasar surveys, more structures might be found, potentially including ones even larger or more geometrically regular than the giant arc. The structure's discovery has prompted other researchers to search for similar features in existing data. Are there other arcs or rings at different distances that haven't been recognised? How common are these symmetric large-scale structures? If the giant arc is unique, that suggests it's an extremely rare fluctuation, possibly problematic for cosmological models. If similar structures are more common, that would be even more challenging to standard theory. Lopez has emphasized that the giant arc, along with other large structures, suggests we need to reconsider the cosmological principle at some level, not necessarily abandoning it entirely, but perhaps acknowledging that homogeneity might emerge only at even larger scales than currently expected, or that there are subtleties in how structure forms that allow larger coherent features than simple models predict. The scientific response to the giant arc has been mixed, as is appropriate for controversial findings. Some cosmologists see it as strong evidence for tension with standard models, potentially requiring new physics. Others are more cautious, suggesting that more detailed analysis and additional observations are needed before drawing strong conclusions. This debate is healthy, reflecting how science handles unexpected observations that challenge existing frameworks. As we continue our journey through the larger structures, the giant arc stands as a reminder that the universe continues to surprise us, that observational astronomy keeps finding phenomena that theoretical cosmology must struggle to explain, and that the interplay between observation and theory drives progress in understanding the cosmos. In 2016, astronomers analysing data from the Baryon Oscillation Spectroscopic Survey, or BOSS, announced the discovery of yet another enormous structure. The BOSS Great Wall, spanning about 1 billion light-years, was found lurking in data that had been publicly available for years, hidden in plain sight until careful analysis revealed its presence. The BOSS survey is one of the largest galaxy redshift surveys ever conducted, mapping the three-dimensional positions of more than 1 million galaxies. Its primary goal was to measure baryon acoustic oscillations, subtle patterns in galaxy clustering that provide precise measurements of cosmic expansion history. But the survey's comprehensive mapping of galaxy positions also makes it ideal for discovering large-scale structures. The BOSS Great Wall was identified by looking for regions of enhanced galaxy density, volumes of space containing more galaxies than average. The structure spans roughly 30 degrees of sky, and given its distance of about 4.5 billion light-years, this angular extent translates to a physical size of about 1 billion light-years. While not as large as the Hercules-Corona Borealis Great Wall or the Giant Arc, it still approaches or exceeds the theoretical homogeneity scale, making it another example of potentially problematic large-scale structure. What's particularly interesting about the BOSS Great Wall is how it was found. Unlike structures discovered through special tracers like gamma-ray bursts or absorption systems, the BOSS Great Wall was found in straightforward galaxy survey data. This suggests that large structures might be more common than we realise, potentially hiding in datasets waiting to be discovered through careful analysis. The structure's detection required sophisticated statistical methods to distinguish genuine overdensities from noise and cosmic variance. Galaxy surveys don't uniformly sample all of space. They have selection effects and incompleteness that can create apparent structures that aren't real. Verifying that the BOSS Great Wall is a genuine structure rather than an artifact required careful comparison to mock catalogues, simulated galaxy distributions generated from cosmological models that include all the survey's selection effects and limitations. These comparisons showed that while structures of this size are rare in standard cosmological simulations, they're not impossibly rare. The Boss Great Wall sits near the tail of the distribution of structure sizes, unlikely but not so unlikely that it definitively contradicts standard models. This places it in an interesting category, large enough to create some tension with theory, but not so large that it demands immediate revision of cosmological principles. The Boss Great Wall also provides opportunities for detailed study because it was discovered in a comprehensive galaxy survey rather than through sparse tracers. Astronomers can examine the properties of galaxies within the wall, studying their masses, colours, star formation rates and environments. This allows tests of how galaxies evolve within large-scale structure, and whether galaxies in these enormous filaments differ systematically from galaxies in more typical environments. Early studies suggest that galaxies in the Boss Great Wall are somewhat more massive and less actively forming stars than average, consistent with expectations for galaxies in high-density regions. Dense environments tend to have more massive galaxies because mergers are more common, and star formation tends to shut down in such environments as galaxies consume their gas supplies and external processes strip gas away. But the Boss Great Wall is large enough that different regions within it have different densities and properties. Some regions are dense cluster cores with massive galaxies and little star formation. Other regions are lower density filaments where star formation continues. This diversity within a single large structure provides a natural laboratory for studying galaxy evolution across different environments. The discovery of the Boss Great Wall, along with other structures found in Boss data, has prompted a reassessment of how common large structures are. If multiple billion light-year structures exist within the volume mapped by Boss, then such structures might be more common than early theoretical work suggested. This could indicate either that our theoretical calculations of maximum structure size need revision, or that our observable universe happens to be in a slightly overdense region with more large-scale structure than average. Determining which explanation is correct requires comparing observed structure frequencies to detailed simulations. How many large structures do we observe per unit volume? How many do simulations predict? If observations significantly exceed predictions, that would suggest theoretical problems. If they match reasonably well, that would support the view that observed structures, while large, are within the range of standard model predictions. Current comparisons suggest mild tension but not clear contradiction. Large structures are somewhat more common in observations than in simulations, but the difference is not overwhelming. More complete surveys covering larger volumes of space will help resolve this question, providing better statistics on structure frequencies and allowing more definitive tests of cosmological models. The Boss Great Wall exemplifies how modern surveys with millions of galaxy redshifts enable discoveries impossible in earlier eras. With comprehensive three-dimensional maps, astronomers can systematically search for large-scale structures, measure their properties precisely, and test theoretical predictions quantitatively. This data-rich approach to cosmology has revealed the universe's large-scale organization in unprecedented detail, while simultaneously uncovering structures that challenge our theoretical understanding. As we've now encountered multiple structures that challenge cosmological expectations, the Hercules-Corona Borealis Great Wall, the Giant Arc, the Giant GRB Ring, the Sloan Great Wall, the BOSS Great Wall, and others, a crucial question emerges. How common are these rare structures? If standard cosmology predicts such structures should be extraordinarily uncommon, but we observe several of them within our limited observable volume, does that constitute a serious problem for the theory? This question of frequency is fundamental to evaluating whether large structures truly contradict cosmological models. Finding one impossibly large structure might be dismissed as an extreme statistical fluctuation, a 1 in a billion chance occurrence that happened to appear in our observable universe. But finding multiple such structures makes the statistical fluke explanation less credible. At some point, encountering enough supposedly rare events suggests either that they're not actually as rare as theory predicts, or that our observable universe is systematically different from typical regions of the cosmos. Cosmologists approach this question by calculating what they call the endpoint correlation functions, or the probability distribution of structure sizes in standard models. Given the measured amounts of dark matter, dark energy, and ordinary matter, given the measured properties of initial density fluctuations from inflation, how often should structures of various sizes appear? For small structures like galaxy groups, the answer is _4_ for intermediate structures like rich galaxy clusters. The answer is _5. For very large structures approaching 1 billion light-years, the answer is _6. And for structures of several billion light-years or more, the answer is _7_. The precise probabilities depend on how you define structures and what volume of space you consider. The observable universe contains roughly 4 times 10 to the 80 particles worth of matter. So even extremely improbable events are guaranteed to occur somewhere if the universe is large enough. The question is whether the density of large structures we observe matches what this statistical analysis predicts. Several studies have attempted to quantify this match. One approach is to count large structures in observations and compare to counts in large simulations. Modern simulations can model volumes comparable to our observable universe. So direct comparison is possible. These comparisons generally show that while large structures are somewhat more common in observations than in simulations, the discrepancy is not overwhelming. It's typically described as tension rather than outright contradiction. Another approach examines whether the largest observed structures exceed what simulations ever produce. If simulations running standard cosmology never produce structures as large as the Hercules-Corona Borealis Great Wall, that would be strong evidence of a theoretical problem. But if simulations occasionally produce similar structures, even if rarely, then observations might be consistent with an unusually structured region rather than a failure of theory. Current results suggest that simulations can produce structures of 1 billion light-years, or slightly more, though rarely. The Sloan Great Wall and Boss Great Wall, at around 1 billion light-years, are within this range. Structures substantially larger, like the Hercules-Corona Borealis Great Wall, at 10 billion light-years, are more problematic. Standard simulations don't typically produce anything that large, suggesting either the observations are overestimating the structure's size and coherence, or there's something missing from theoretical models. The giant Archan-Giant GRB ring, at 3 to 5 billion light-years, sit in an intermediate zone. They're larger than what simulations commonly produce, but not impossibly beyond simulation limits. Their existence creates tension without definitively breaking models. There's also a question of how we define quotate for counting purposes. Is the Hercules-Corona Borealis Great Wall one structure or several smaller structures that happen to align? Different definitions lead to different counts. If we use strict criteria requiring strong physical coherence, we might count fewer large structures. If we use looser criteria allowing any significant overdensity to count, we'll count more. The choice of definition affects whether observations match theoretical predictions. Some researchers have proposed that these issues with large structures might indicate we're misunderstanding cosmic variance, the natural statistical fluctuations expected when observing finite volumes. Our observable universe is just one realization of the cosmic density field drawn from a probability distribution. Other regions of space would show different structure realizations. If we happen to observe a region with above-average large-scale structure, that's not a theoretical problem, but just cosmic variance. For now, the verdict remains open. The largest structures create tension with cosmological models, suggesting either that our understanding needs refinement or that our observable universe is somewhat atypical. This tension is productive, driving more precise observations and more sophisticated theoretical work, gradually narrowing the space of possibilities and bringing us closer to understanding how the universe truly organizes matter at its larger scales. The tension between observed cosmic structures and cosmological theory invites reflection on a deeper question. What is the nature of physical law? And what does it mean when observations challenge our theoretical expectations? This question sits at the boundary between physics and philosophy, touching on how we understand natural laws and their limits. Physical laws, as we conceive them, are mathematical descriptions of how nature behaves, relationships between quantities that hold universally across space and time. Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's field equations of general relativity, all these express regularities in nature that we've discovered through observation and experiment, then codified in mathematical form. But physical laws aren't arbitrary. They're constrained by principles like conservation of energy, symmetry requirements, and logical consistency. When we say a structure shouldn't exist according to cosmological models, we're really saying that producing such a structure would require violating principles we believe are fundamental, principles that have been tested extensively and have never failed in other contexts. The largest cosmic structures don't violate conservation laws or require faster-than-light processes. They don't break general relativity or contradict quantum mechanics. What they do is challenge our statistical expectations based on applying these laws to cosmic evolution. They suggest that either our calculation of what's probable is wrong, or the universe is arranged in ways that make the improbable actual. This distinction is important. A true violation of physical law, something that contradicts well-tested principles, would require revolution in physics, a fundamental rethinking of how nature works. But unexpected structures that are merely improbable, rather than impossible, might require only refinement, better understanding of initial conditions, more careful accounting of all relevant processes, improved statistical analysis. Throughout physics history, we've seen both kinds of surprises. The anomalous precession of Mercury's orbit was a genuine problem for Newtonian gravity, eventually requiring Einstein's general relativity to explain. But the unexpected discovery of galaxies beyond the Milky Way, once thought to encompass the entire universe, didn't require new physics. Just expanded appreciation of the universe's scale. The question for large cosmic structures is which category they fall into. Are they like Mercury's precession, harbingers of needed theoretical revolution? Or are they like the discovery of external galaxies, surprising but ultimately consistent with existing physical frameworks once we adjust our perspective? Arguments can be made both ways. Those favouring revolution point to the repeated discovery of structures that challenge size limits, suggesting a systematic problem rather than occasional flukes. They note that both dark matter and dark energy were initially surprising observations that required new physics, so perhaps large structures are similarly pointing towards something fundamental we're missing. Those favouring refinement note that the structures, while large, aren't definitively impossible in standard models, just unlikely. They point to uncertainties in how we define structures, in cosmic variance, and in comparing observations to simulations. They argue that before concluding we need new physics, we should exhaust explanations within existing frameworks. Perhaps the larger structures are teaching us humility about what we can know. Cosmology deals with the entire universe, much of which we can never observe directly. We extrapolate from our observable region to draw conclusions about the whole, but this extrapolation rests on assumptions like the cosmological principle that, while reasonable and well supported, might not be perfectly true at all scales. The universe might be more complex, more variable, more interesting at the larger scales than our models capture. This complexity wouldn't invalidate the laws of physics, but would enrich our understanding of how those laws play out in cosmic evolution. It would be a refinement, deepening rather than overturning existing knowledge. And there's something fitting about this. The universe's larger structures, representing organisation at scales that strain human comprehension, challenging our best theories in subtle ways, remind us that nature retains mysteries even after centuries of scientific progress. Complete understanding might always remain slightly beyond reach, not because nature is fundamentally incomprehensible, but because it's inexhaustibly rich, always holding new phenomena to discover, new patterns to explain, new puzzles to solve. As our exploration of the universe's larger structures approaches its conclusion, it's worth contemplating the limits of cosmological knowledge, the boundaries beyond which observation and theory might never penetrate. Some aspects of the universe might be fundamentally unknowable, not because of technological limitations, but because of the universe's nature itself. The most obvious limit is the cosmological horizon. Light from regions beyond about 46 billion light-years has not had time to reach us and never will, because cosmic expansion is accelerating. This means we can never directly observe most of the universe. If the cosmos is infinite, as some models suggest, then our observable portion represents an infinitesimal fraction of the whole, a single point in an infinite expanse. This observational horizon creates profound limitations. We can never verify whether the cosmological principle holds universally, because we can only test it within our observable region. The largest structures we observe might be typical of the entire universe, or might be unique to our cosmic neighbourhood. We'll never know which through direct observation. Some physicists appeal to anthropic reasoning, arguing that physical laws must be compatible with intelligent observers, because otherwise we wouldn't exist to ask the question. If the cosmological constant were much larger, structure wouldn't form. If fundamental forces were significantly different, atoms and chemistry wouldn't work. We observe the laws we do because they're among the few that permit life. But this reasoning, while intriguing, doesn't provide the same satisfying understanding as derivations from deeper principles. It leaves a sense that fundamental questions remain unanswered, that we've hit a boundary where, because we exist, is the only explanation available. The largest cosmic structures touch on all these limitations. Their existence challenges our theoretical understanding, but definitively explaining them might require knowledge beyond what observation permits. If these structures require understanding of inflation's detailed mechanism, we face the challenge that inflation occurred in an epoch we can't observe directly. If they require knowing whether our observable universe is typical, we face the challenge that we can only observe one universe region. If they point toward new physics, modified gravity or variations in dark energy, testing such ideas requires precision measurements at the largest observable scales, precisely where measurements are most difficult and uncertain. Observational evidence might always remain ambiguous, unable to definitively distinguish between alternative explanations. These limitations aren't reasons for despair, but for appropriate epistemic humility. Cosmology has made extraordinary progress over the past century, progressing from vague speculations about the universe to precise measurements of its age, composition, and geometry. We've mapped cosmic structure across billions of light years, traced cosmic history from the Big Bang to the present, and developed theoretical frameworks that explain vast ranges of phenomena. But complete knowledge might be impossible, not because the universe is inherently mysterious in some mystical sense, but because our observational access is limited, and some questions lie beyond what any observation could answer. The larger structures might represent phenomena near the edge of explicability, where what we can observe barely constrains what's theoretically possible. Yet within these limits, much can still be learned. Better observations will clarify whether large structures are as common and as large as current data suggests. Improved simulations will test whether refinements to standard models can explain observations without new physics. Theoretical work will explore what kinds of modifications to cosmology, if needed, would be most natural and consistent with other observations. The dance between observation and theory will continue, each informing and constraining the other, gradually narrowing the range of possibilities even if definitive answers remain elusive. This is how science often works at its frontiers, not providing final answers but progressively improving understanding, replacing vague ideas with precise models, and identifying which questions can be answered and which might forever remain open. And there's beauty in this process of exploration, in the gradual illumination of cosmic mysteries, even if complete illumination remains beyond reach. The larger structures invite us to think deeply about what we can know, how we can know it, and what mysteries might always lie beyond our grasp, calling to us from across billions of light years of space and billions of years of time. Throughout this journey, we've contemplated structures so vast that human minds struggle to grasp them. 10 billion light years, 3.3 billion light years, 5 billion light years. These numbers are so large that they lose intuitive meaning, becoming abstract quantities rather than comprehensible distances. Yet there's value in attempting to understand them, in situating ourselves within this vast cosmic architecture. Consider the scale ratios involved. A human is roughly 1.7 meters tall. Earth is about 13 million meters in diameter, making it roughly 10 million times larger than a human. The Sun is about 100 times larger than Earth. The distance between stars in our galactic neighbourhood is roughly 100,000 times the Sun's diameter. The Milky Way galaxy is roughly 100,000 light-years across, and the Hercules-Corona Borealis Great Wall is about 100,000 times larger than the Milky Way. Each step in this scale hierarchy represents a factor of roughly 100 to 100,000. We're separated from the largest structures by 8 or 9 orders of magnitude steps, each representing a conceptual leap comparable to jumping from human scale to Earth scale or from Earth scale to stellar scale. The cognitive distance from our immediate experience to cosmic structure is vast, yet remarkably, we can bridge this distance intellectually. Human minds, confined to human-scale bodies living on a single planet, can nevertheless conceive of, observe, and theoretically model structures billions of light-years across. This ability is extraordinary when you consider it. Nothing in evolutionary history prepared us to think about such scales. Our ancestors needed to understand hunting distances, gathering ranges, social group sizes, all measured in meters to kilometers. That we can extend this understanding to cosmic scales represents a kind of cognitive achievement unique to human intelligence. This achievement rests on mathematics and abstract reasoning. We can't visualize 10 billion light-years in the same way we visualize 10 meters, but we can reason about it, can build mathematical models that describe how matter behaves at such scales, can compare theoretical predictions to observations, and can gradually build understanding even of realms far beyond direct experience. This perspective can feel either humbling or meaningless. Humbling because it reveals how small and brief human existence is compared to cosmic scales and time scales. Meaningless because if we're so tiny compared to the universe, perhaps nothing we do ultimately matters in the grand scheme. But there's another perspective, one that finds meaning precisely in this vast difference of scale. We're part of the universe, arrangements of atoms following physical laws, and yet we're arrangements capable of understanding the whole. The universe has, through us, become conscious of itself, capable of measuring its own extent and contemplating its own history. This self-awareness, regardless of the scales involved, represents something profound. The larger structures aren't just objects external to us that we study. They're made of the same matter we're made of, atoms forged in stars and scattered through space. The carbon in our bodies was synthesized in stellar cores. The hydrogen is from the Big Bang itself. We're quite literally made of star stuff, organised into patterns complex enough to wonder about our origins, and the structures themselves arose through simple processes repeated over vast scales and times. Gravitational instability, the tendency of over-dense regions to attract more matter and become denser, working over billions of years, created the cosmic web. Complexity from simplicity, organisation from chaos. This parallels the emergence of life from chemistry, of consciousness from neuronal activity, of civilization from individual human actions. The universe seems to have a tendency toward creating pattern and structure at every scale. Perhaps meaning lies not in size, but in pattern, in complexity, in the ability of systems to organise and understand themselves. Humans might be tiny compared to galaxies, but we're vastly more complex, with internal organisation that exceeds anything in cosmic structure. A single human brain contains more synaptic connections than there are stars in a galaxy. Consciousness, whatever its physical basis, represents a kind of complexity that doesn't exist in galaxy clusters no matter how large. So while cosmic structures dwarf us physically, we match or exceed them in other dimensions: complexity, information content, self-awareness. The universe contains both kinds of remarkable phenomena, the overwhelmingly large and the intricately complex. And we happen to be examples of the latter contemplating the former. The larger structures invite us to expand our thinking beyond human scales, to conceive of the universe as it truly is, rather than as it appears from our limited vantage point. This expansion of perspective is valuable regardless of size comparisons, a stretching of imagination and understanding that enriches human existence, even if it doesn't change our physical place in the cosmos. As we near the end of our exploration, it's worth looking forward to what future observations might reveal about the universe's larger structures. Several major astronomical surveys and missions planned for the coming decades will dramatically improve our ability to map cosmic structure and test whether the largest observed structures are truly problematic or merely surprising within standard cosmology. The Vera Rubin Observatory, beginning operations in Chile, will conduct the legacy survey of space and time, imaging the entire visible sky repeatedly over 10 years. This survey will detect billions of galaxies, creating the deepest, widest map of the universe ever made. The enormous data set will allow astronomers to identify large-scale structures throughout the observable universe and measure their frequency with unprecedented precision. If large structures are more common than standard models predict, Rubin Observatory will find many more examples. If they're as rare as theory suggests, it will clarify that known large structures are statistical outliers rather than indicators of systematic problems. Either outcome advances understanding, either by revealing tension that requires theoretical work, or by confirming that current models, while surprised by individual structures, are statistically correct. The European Space Agency's Euclid mission, launched in 2023, will map the geometry of the universe through weak gravitational lensing and galaxy clustering. Euclid's measurements will constrain dark energy properties with unprecedented precision and provide detailed maps of matter distribution across cosmic time. These maps will reveal whether the cosmic web structure matches predictions or shows anomalies at large scales. Euclid's particular strength is measuring how structure evolves over time by observing galaxies at different distances and hence different cosmic epochs. If large structures formed earlier or grew faster than expected, this temporal evolution will reveal it. Understanding when the largest structures assembled provides crucial constraints on formation mechanisms and initial conditions. The Nancy Grace Roman Space Telescope, planned for launch later this decade, will conduct wide-field infrared surveys, detecting galaxies too faint for ground-based telescopes. Roman's deep imaging will extend structure mapping to greater distances and earlier cosmic times, potentially revealing whether structures as large as those we observe locally existed in the earlier universe, or whether they're more recent developments. These missions will also improve measurements of the cosmic microwave background's subtle features. Observations from telescopes like the Atacama Cosmology Telescope and the Simons Observatory continue refining our understanding of initial density fluctuations from inflation. If large-scale structure anomalies trace back to unusual initial conditions, improved microwave background measurements might detect subtle signatures that explain the structure's origins. Ground-based radio telescope arrays like the Square Kilometre Array will map neutral hydrogen throughout cosmic history, providing a different view of a large-scale structure less biased by the visible light from galaxies. Hydrogen traces all matter, not just where stars are formed, potentially revealing structures invisible to optical surveys. Improved simulations will also play crucial roles. As computational power increases, cosmologists can run larger simulations with more particles, better resolution, and more realistic physics. These simulations will test whether refined models can produce large structures matching observations while still satisfying all other cosmological constraints. Machine learning and artificial intelligence are increasingly applied to cosmological data analysis. These tools can identify patterns in vast data sets that traditional analysis might miss, potentially revealing additional large structures or subtle correlations that inform theoretical understanding. They can also quantify uncertainties and systematic effects more rigorously, improving confidence in whether observed structures truly challenge theory. Multi-messenger astronomy, combining electromagnetic observations with gravitational waves and neutrinos, might provide new ways to probe large-scale structure. Gravitational wave observations from colliding black holes and neutron stars reveal where these systems exist throughout the universe. As detectors improve and numbers of detected events increase, gravitational wave sources will trace cosmic structure complementing electromagnetic observations. Within the next decade or two, we'll have much clearer understanding of whether the largest structures represent serious challenges to cosmology or are explained within refined standard models. The observations will either strengthen the case for new physics if more large structures are found and their properties deviate systematically from predictions, or will resolve the tension, showing that initial concerns were overstated once better data and analysis became available. What we won't have, likely, is complete certainty. Cosmology deals with unique events and unrepeatable histories. We observe one universe from one location, and many questions might remain permanently ambiguous. But the range of possibilities will narrow and our understanding will deepen, bringing us closer to comprehending how the universe organizes matter at its largest scales. These future observations will also surely bring surprises we haven't anticipated. History suggests that whenever we dramatically improve our observational capabilities, we discover unexpected phenomena. The larger structures currently known might seem modest compared to what future surveys reveal. Or we might find that the universe is less structured at large scales than we thought, that observed structures are maximal and nothing larger exists. Either way, the journey of discovery continues. The larger structures might remain mysterious for decades, or their explanation might emerge from unexpected directions. Perhaps they'll become footnotes in future cosmology textbooks, interesting but ultimately explicable anomalies. Or perhaps they'll be recognized as harbingers of a theoretical revolution still unfolding. We'll learn which as observations and theory advance, as the conversation between what we see and what we understand gradually converges on truth. We've travelled through 10 billion light-years of cosmic structure, explored the tensions between observation and theory, contemplated the limits of physical law and human knowledge. We've encountered structures that shouldn't exist according to our best models yet do exist, mapped and measured, stretching across substantial fractions of the observable universe. And as we prepare to conclude this journey, perhaps the most profound realization is that questions without definitive answers can be as valuable as those we can answer completely. The largest cosmic structures represent this kind of productive uncertainty. We know they exist. We've observed them, mapped them, calculated their sizes and statistical significance, but we don't fully understand them. We can't confidently say whether there are extreme statistical fluctuations within standard cosmology, whether they require modifications to our theoretical models, or whether they're telling us something even deeper about the universe's fundamental nature. This uncertainty isn't a failure of science, but a sign of its vitality. Science doesn't progress through accumulating certainties, but through questioning, testing, refining understanding. The history of science is filled with moments when observations challenged theories, creating tensions that drove theoretical development. Sometimes the theories were refined to accommodate observations. Sometimes observations were reinterpreted as better understanding developed. Sometimes entirely new frameworks emerge to explain previously mysterious phenomena. The larger structures are currently in that uncertain space where observations and theory don't quite agree. This tension is uncomfortable for those who prefer definitive answers, but it's generative for those who see science as an ongoing conversation between humanity and nature. The structures pose questions that current cosmology struggles to answer, and those questions inspire new observations, new analyses, new theoretical ideas. There's beauty in this process of inquiry itself, separate from whatever answers eventually emerge. The ability to ask deep questions about the universe, to gather evidence bearing on those questions, to construct mathematical frameworks attempting to explain observations. This entire scientific enterprise represents something extraordinary about human consciousness. We're pattern-seeking beings, meaning-making creatures, and the largest structures provide patterns and meanings we're still working to fully comprehend. The structures also embody a kind of aesthetic grandeur, independent of their theoretical implications. 10 billion light-years across, patterns stretching across the visible universe, organizations of trillions of galaxies into coherent arrangements. These aren't just numbers or scientific puzzles, they're manifestations of cosmic architecture. Order emerging from chaos through simple physical laws working over unimaginable spans of space and time. There's something satisfying about contemplating such vast structures, about imagining filaments of galaxies spanning distances light takes billions of years to cross. It puts our existence in perspective while simultaneously revealing that we're part of something immense and intricate. The atoms in our bodies were forged in stars. Those stars formed in galaxies. Those galaxies organized into the cosmic web. We're connected to the larger structures through chains of physical causation stretching back to the Big Bang. This connection isn't mystical but physical, mathematical, comprehensible through science yet still inspiring wonder. Wonder at scale, at complexity, at the universe's tendency to organize matter into patterns at every scale, from atoms to cosmic walls. Wonder at our ability to discover and understand these patterns despite being confined to a single small planet. Wonder at the questions that remain open, inviting future exploration and deepening understanding. Perhaps the larger structures will turn out to be explicable within slightly refined versions of current cosmological models. Perhaps they'll require more substantial theoretical modifications. Perhaps they'll remain mysterious longer than we'd like, awaiting observations or insights not yet imagined. Whatever the eventual explanation, the journey toward understanding has already enriched cosmology and will continue doing so. And there's a kind of contentment available in accepting uncertainty, in appreciating that not all questions have immediate answers, that some mysteries invite long contemplation rather than quick resolution. The larger structures have occupied cosmologists' attention for years, and will likely continue doing so for years more. This sustained engagement with difficult questions, this willingness to live with productive uncertainty, represents intellectual maturity and commitment to genuine understanding over facile explanations. As we move toward our closing, having explored the larger structures from multiple angles, having considered their discovery, their properties, their challenges to theory, and their invitation to wonder, we can appreciate them as both scientific puzzles and cosmic marvels. They're problems awaiting solution and phenomena deserving contemplation. They're at once knowable through science and mysterious in their full implications. They're the universe at its most vast, and somehow we tiny creatures on a small planet can conceive of them, measure them, and wonder at their existence. And so we've reached the end of our journey through the largest structures in the universe, these impossible walls and arcs and filaments spanning billions of light years. Thank you for staying with me for these 2.5 hours, for drifting alongside me through scales so vast they strain comprehension, through mysteries that challenge our best theories, through the beautiful complexity of how the universe organizes itself at the grandest scales. We've travelled from our small Earth across billions of light years to structures like the Hercules-Corona Borealis Great Wall, 10 billion light years wide, and the giant arc. 3.3 billion light-years of symmetric structure that shouldn't exist according to the cosmological principle. We've explored how these structures formed from quantum fluctuations in the first fraction of a second after the Big Bang, how gravity amplified tiny density variations into the cosmic web of filaments and voids, and how the largest structures push against theoretical limits on how much organisation the universe should have had time to create. We've contemplated what these structures mean for cosmology, whether they require new physics or merely better understanding of existing frameworks, whether dark energy or modified gravity or unusual initial conditions might explain them. And we've reflected on the limits of knowledge, on questions that might never receive definitive answers, on the beauty of productive uncertainty when observation and theory don't quite align. The question I asked at the beginning, why these larger structures shouldn't exist, has been answered as honestly as current science allows. They shouldn't exist because there hasn't been enough time since the Big Bang for gravity to organise matter into structures this large, because the cosmological principle says the universe should be homogeneous at such scales, because our best simulations rarely produce anything comparable, yet they do exist. The gamma-ray bursts trace them, the galaxies map them, the statistics confirm them. And this tension between theoretical expectation and observational reality is where science happens, where understanding advances. Perhaps future observations will resolve this tension, revealing that the structures aren't as large or as coherent as they initially seemed, or showing that refined models can explain them comfortably. Perhaps they'll deepen the mystery, finding more such structures and confirming that something in our cosmological framework needs revision. Either way, we'll learn. Either way, understanding will grow. If you've enjoyed this slow drift through cosmic mysteries, a like and subscribe helps reach others seeking the same peaceful way to learn about the universe. Your support makes these long-form documentaries possible, makes it possible to take time exploring complex ideas without rushing, to contemplate both the science and the wonder. To those who return to these journeys regularly, who trust me to guide you through space and time as you drift towards sleep, thank you. This community of curious minds is why these videos exist. Wherever you are in the world right now, I hope you're comfortable. I hope your breathing has found a slow, natural rhythm, each breath deeper and calmer than the last. I hope your thoughts have quieted, that the day's concerns have receded to distant murmurs, that your body feels heavy and warm, released from the need to hold tension or maintain alertness. You've done well today. You've made it through, and now you can rest. Look up at the night sky if you can see it, or imagine it if you cannot. All those stars, each one a sun perhaps with planets. All those galaxies, billions of them scattered through space. And beyond what we can see individually, the vast filaments of the cosmic web, invisible to naked eyes but real and measurable, structures so large they challenge our understanding yet exist nonetheless, patient and vast, stretching across billions of light-years of dark space. Somewhere in that darkness, 10 billion light-years from here, light is passing through the middle of the Hercules-Corona Borealis Great Wall. That light began its journey long before Earth formed, before our sun ignited, before our galaxy assumed its current spiral shape. It's been travelling all that time, crossing through galaxy after galaxy, through vast stretches of near-empty space, witnessing the slow evolution of cosmic structure over billions of years. And in our small observatories on Earth, with our instruments and telescopes and patient observation, we've detected that light, measured its patterns, deduced from its properties that matter is organised in ways we didn't expect. This ability to reach across such distances, to understand structures so vast and ancient, is remarkable. You're part of a species that can do this, that can observe and comprehend the universe at its largest scales. That's worth appreciating as you drift towards sleep. Sleep well tonight, knowing that above you, around you, extending in all directions farther than light can travel in the universe's lifetime, cosmic structure exists, galaxies organised into patterns both beautiful and mysterious, conforming to physical laws we understand while simultaneously challenging our theoretical expectations. Dream, if you dream, of filaments billions of light years long, of walls of galaxies spanning fractions of the visible universe, of the slow dance of matter under gravity's gentle but inexorable pull. Dream of the cosmic web, intricate and vast, connecting everything to everything across impossible distances. Good night.